A warm good morning to all my dear students. I shall now give a quick recap or a review of merge sort and the quicksort algorithm. This is an attempt to clarify your small doubts that you would have had while understanding these two methods. First, let's understand the algorithm design strategy, which is divide and conquer. This is one of the very important algorithm design strategy. Merge sort and the quicksort are typical examples of divide and conquer strategy. We'll understand term by term. The first is divide. The given problem is divided into smaller subproblems. We keep dividing the subproblem until we reach a stage wherein the size of the subproblem is small enough to be handled directly. S. The next is conquering each of the subproblems. That is, I need to solve each of these subproblems. Very often is that being done in a recursive manner. And lastly, should I combine the solution of the subproblem to get the solution to the original problem? So hence the whole philosophy is divide the problem, solve each the subproblem, and then combine the solution into this solution to the original problem. Now let's take up the merge sort method. The sorting is putting the numbers in order. So now I'm given with an array to sort the numbers. So we'll apply the divide and conquer strategy. The first is division. Very simple strategy. Herein I just divide the problem exactly in the middle. Now the next thing is conquering. So each of the subproblem, I just have to sort them out. It's a subproblem. I should have a means to sort it out. Now lastly, combining the sorted subarrays have to be merged to form a single sorted array. And please note that merge is not appending. So I'll have to do some extra work to merge two sorted arrays into one sorted array. This is the algorithm. So this is a recursive algorithm. So the name of the algorithm is merge sort. The name of the array is A, and the elements to be sorted run from the position P through the position R. Any recursive must have a termination condition. I keep applying the strategy, the divide and conquer, until I have more than one element. So this condition P less than R ensures that there is at least more than one. If not, I will not be going for the division. Now where am I dividing? I just go to the middle of the element, the array. Now I have two arrays, one running from P to Q, another one Q plus 1 through R. So I call the same algorithm merge sort to sort the array from P to Q, another one from Q plus 1 to R. Now I have this array to be sorted, this array to be sorted. Should I now combine them, for which I call another function? It is the merge. So this is where am I trying to divide, trying to conquer each subproblem by calling the same algorithm. Here am I combining the subarrays into a single one. Now this is a closer look at the merging here. So this is what I'm given with. This is one sorted array. This is another sorted array. These have to be merged into a single one. Now the idea is look at the smallest of one subplace with the smallest of the element of the other subplace. Of these two, whichever is the smallest, put it into the resultant array. So, and I keep doing this, comparing smallest of both of this array until I have numbers in both of this subplace here. So this is the whole idea. Now, having had a feel of a merge sort, the next is we need to determine how good is my merge sort algorithm. Now I shall figure out how much work is done in each of the phases: divide, conquer, and combine. Divide, I am really doing nothing, just just for that I go in to the middle of the array. So hence it is the time is of the order 1, or is that a constant. Now conquering, I have two sub-problem, each of size n by 2. So hence the time is, it is time required to solve a problem of size n by 2 such there are two sub-problem, and hence it is 2tn by 2. Now combining is not very trivial. I'll have to do a substantial work there here, the merge operation. So in the merge operation, I look at every element there here, and hence the time is of the order n. So using these two, so this recurrence formula is arrived at. Now, the beauty of splitting the problem into two equal halves there here. So this is the best possible that one can expect whenever we're trying to divide the problem, because when I divide and exactly in the middle, if the division happens somewhere in the middle, initially I have a problem of n. When I divide, each sub-problem will be of size n by 2. Further division, each sub-problem will be of the size n by 4, n by 8, n by 16, so on until I reach stage 1. For any value of n, by the time I reach a stage of 1, the number of times I need to split will be equal to log n. So the depth of recursion will be log n, and this is the best that anybody can expect in any divide and conquer strategy, and the merge sort does have this. Now for this merge sort, this is running time is insensitive to the input. That means that it doesn't depend on the type of the input, doesn't exhibit a worst, best, average case, all in one. So hence it is guaranteed to run in time n log n for any input. So, and you can get a feel of this log n because we said that every time I do, there will be a log n number of splits, and each time I'll be examining all the elements, and thus the total time will be n log n. So the recurrence formula can be solved using Master's theorem, and you will get that to be n log n, and this is a stable algorithm. But one downside of this algorithm is that this requires an additional amount of memory n spaces. Why? Because I cannot do merging in place. I need an additional array to perform the merge operation. This is one of the drawback of the merge sort algorithm. So the next is we'll start with the quicksort algorithm here. So the name itself says that it is the quickest sorting method, or the best possible sorting method on an average. So we'll again apply this divide and conquer. The first is I divide. So the division, and the word that we use is not the division, I use the word partition. So I should partition the array into two groups. So whenever I say partition, I should have some reference. Say in our class, I would want to partition into two groups. I should have some parameter. I should say I'm using the gender. So it is all girls to one group and all boys to another group. Similarly, so here I choose one element to serve as the parameter. So for that number, what I do is all the numbers whose value is less than this, I'll put it to the left side. All the numbers whose value is greater than this, I'll put it to the right side. When I'm able to do this here and place my the key element or the pivot element at this position, I say that have achieved partitioning. This is what it means to have a partitioning. And the beauty is that when I place the pivot element at this position, that means that the pivot element has found its final position. It doesn't have to be disturbed hereafter. So that means that every time I'll be putting one element into its final position. So this is the conquering. So each partition sublist have to be sorted by calling the quicksort recursively. Now the combining, because each sorted lists are sorted individually here. So the combining, I really don't have any work to be done. So now we can compare this with that of the merge sort. So the merge sort, I didn't have anything to do, but in a quicksort I have a lot of work to do in a division. That is, I should do a partition. Now the conquering, it's the same thing because each of the partitions have to be sorted separately. Now combining, merge sort, combining has got to do a lot of work because each of the two sorted arrays have to be merged into a single one. But in a quick sort, I don't have anything to be done in a combining. So that herein in the merge sort, lot of work to be done in combining than in division. In a quick sort, lot of work to be done in the division and nothing to be done in the combined stage. So this is one way that I can contrast the quick sort with the merge sort. Now this is the quicksort algorithm. So the name of the algorithm is quicksort. I need to sort the element, the array A, and the elements run from the position through from P to R. And any recursion must have a termination condition. I keep doing this until I have, as long as I have more than one element. Now I call for a partitioning. Now it tells me what is the position of the pivot element, the key element. So the position is Q, and in this partitioning, because the first element is chosen as the pivot element. Once I do a partitioning and the pivot element is at the position Q, they here. Now I have two lists, the one running from P to Q, another one running from Q plus 1 to R. So I do this, I call quick sort for the first sort, the first sublist P to Q, and another call for the other sublist. So this is the worst case partitioning they here. The worst case input in my partitioning, my n number of numbers they here. One partition will have only one element, the other will have n minus 1. And when I start applying the quicksort for this, again the same thing happens. When I partition this they here, one partition will have only one element, the other one will have n minus 2. And if this were to continue for thereafterwards, then by the time I reach a problem of size n, the depth of recursion would be n. So that is, I'll have to have n number of depth of recursion. Each time I'll have n work to be done. So it's the worst case time complexity happens to be n square. And this is the best case partitioning they here, where the partitioning X happens somewhere in the middle. So that is each partition of the size n by 2 of the first time, the next time it will be of the n by 4, so forth, and they reach a problem of size 1. Whenever this is the situation they here, my depth of recursion will be log n and the time will be n log n. Now the next is, the last issue is, how do I choose the pivot element, because this to a greater extent decides how well the quicksort algorithm behaves on the given input. So far what we've chosen is the very simplest method, wherein the first element is chosen as the pivot element. Similarly, the other strategies to choose the pivot element are just take the last element as the pivot element, or can I use the median of all array elements, because this is desirable because I want the partitioning to happen somewhere in the middle of the array. So this would be the best one, but it takes a lot of time. And an improvement of this is that just find the median of the first, middle and the last element in an array. So this will also give a better partitioning. Or can you choose an element randomly to serve as the pivot element? So these are the different ways, and then people have done a lot of work, a lot of research on each of this method and trying to find out how well the quicksort algorithm behaves when each of these strategies are chosen to pick the pivot element. So this is all for you now. Now with this to understanding, now solve the exercise problems that are given, and this should give you enough input and the knowledge to prepare for these two algorithms for the coming exams. Thank you, students.